basic rational functions. These are we're not really going to get too in depth just because we can't, but the rational function example is just any function that's in the form of r of x is equal to p of x over q of x, where p of x and q of x are polynomials. All right, so the only thing that we're going to do before the end of this unit is learn about vertical asymptotes, horizontal asymptotes, and what's called end behavior. So we're keeping it simple because there's some things that we have to learn about polynomials in the second unit that that are necessary in order to understand rational functions. Question?
Yeah, could you just say what a polynomial is again? I forget like definitions of things.
Oh yeah, polynomial is any function that's in the form of ax to the nth power plus bx to the n minus 1 plus cx to the n minus 2 and so on. What that just means is, for example, you might have something like 5x to the 4th plus 3x to the 3rd plus 2x to the 2nd, something along those lines. Right.
Okay,
I mean, yeah, the notation makes it seem harder than it is, just because there's really no nice way of writing it. But that's really all there is to it. Kind of painted myself into a corner here. Okay. So you could see for the vertical asymptote problem, there's a pretty clear-cut case of polynomial over polynomial if you follow this definition. I mean, it's clearly not as complicated as that example I just wrote, but it's something that has variables, powers, coefficients, and all that jazz. Right? If you want to find a vertical asymptote, there's a couple ways to do it. One way involves, you guessed it, Desmos. The other way involves an algebraic approach. Right? So the algebraic approach set your denominators equal to 0. I don't know why I pluralized that. Denominator. Solve for x. All right. The location that you arrive at or you determine will be the location or locations of the vertical asymptote. Okay. The vertical asymptote itself is a line that the curve is going to approach, specifically a vertical line. So vertical line that the curve approaches. All right. Some definitions say an asymptote is a line that a curve approaches but never touches, but that's actually incorrect. You can touch asymptotes. It's just there's some instances where it wouldn't happen for other reasons, but not because it's an asymptote, just because of the nature of functions. So in this case, what I would do is I would take my x squared minus 4, set it equal to 0, and solve. Now this is a basic binomial. It's nothing too crazy. In terms of quadratics, I mean, you might think about things like factoring, completing the square quadratic formula, all of which we're going to review in the second unit. But it's even more basic than that because it's in binomial form. I could just add 4 to both sides and get x squared equal to 4. And then when I want to solve for x, I would just take the root of both sides. And we know from years past, semesters past, maybe days past, days of future past, that the square root of 4 is not just a 2, it's also a negative 2. So we would say plus or minus 2. that is the location of the vertical asymptote, which we abbreviate with a VA. Surprise, surprise. All right. Let me give you the visual on that. We got a visual on the bogey. So what you would say is R of X, or you could use anything of X, no matter Y of X, F of X, E of X. Stay away from X of X, I guess. So 5 minus X over X squared minus 4. A fun looking graph. If I plot X equals 2 and X equals -2, you see vertical lines up here. I'm going to just change the format a little bit, make them dashed. Makes it pop a little bit more, you know. But my definition of a vertical asymptote is a vertical line that the curve approaches. We've actually seen this before. We did it a few problems ago. But if you look at this curve, you can see, I mean, if I'm just kind of focusing on this piece here, it appears that that curve is approaching it. I mean, I can keep zooming and scrolling and all that. It's approaching, it's getting closer and closer. It's not getting there very fast, but it's getting closer and closer. And it's doing that in multiple places. It's happening here, it's happening here, and it's happening here. All right. So that's an instance of a vertical or a pair of vertical asymptotes, but simply determined algebraically by setting the bottom of your fraction equal to 0 and solving. Right. Now, let's say your algebra skills aren't up to snuff and you have a little difficulty solving an equation like x squared minus 4 is equal to 0. One thing that you could do is graph just that equation and see where it's equal to 0, as in where it crosses the x-axis. And that'll give you your solution. Right? You could do that for any equation that's set equal to 0. You're just looking for x-intercepts. Right? So you just, with Desmos, you just tap on those x-intercepts and you're good. All right. Title of the class is not algebra. So I don't want you to get bogged down with the algebra. If you find that there's something that requires a solution and you have a choice between algebra and Desmos and you don't know how to do the algebra, then your choice is clear. All right. So just keep that in mind. Be mindful of that. All right. Now the other type of asymptote would be a horizontal asymptote. And you guessed it, it's the horizontal line that the curve approaches. We got some fun rules for that one. But oftentimes, you could just pick it out just by looking at it. Like, for example, if I tell you that this function approaches a horizontal line somewhere, you look at it and say, oh, I wonder. It looks like it might be approaching the x-axis, but I'm not 100% sure. On this side, maybe you say, yeah, it could be approaching the x-axis, but I'm not 100% sure, but at least you're suspicious. You look at it and say, okay, whatever it is, it's somewhere in the neighborhood of the x-axis. All right, but we do have some rules that'll become clearer when you get to calculus and you start talking about limits. And that is these M and N rules, right? So we have the full-blown formula for a rational function in its full glory. The M and N values represent the highest power in the top and bottom of the fraction. So the M is the highest power in the numerator. N is the highest power in the denominator. A sub m is the leading coefficient in the numerator. a sub n is the leading coefficient in the denominator. All right. Those are the only things that are kind of unique to this approach. Once you identify those pieces of information, you'll be able to pick out your horizontal asymptote. Right. So looking at the first example, it says r of x is equal to 1 over x. We're first going to classify based off of the relationship between the powers. Right. So 1, that numerator of 1 has an assumed x to the 0th attached to it. All right. Any number has an assumed x to the 0th attached to it. We'd never write it, but if it's a polynomial, that's assumed because x to the 0th is equal to 1, and 1 times 1 would be 1. All right. That x on the bottom can be written as 1x to the first. So the powers between the top and the bottom, that top power, we call that m. That bottom power, we call that n. We look for the relationship between m and n. All right. In this case, m is less than n. So therefore, we would say, so we look at all the conditions that we have, our classifications. M could be less than n, m could be equal to n, or m can be more than n. In this case, m is less than n, which means our horizontal asymptote is the line y equals 0. So it's really just identify the numbers from the expression and pick out the appropriate result based off the classification. So in the next example, you see a 2, you see an x, right? So that negative x is really negative x to the first power, right? That 2 has an assumed x to the 0th attached to it. That won't be the high power. The high power is the only one I'm interested in, right? So that's my m value. The n value is a 2 here. So in this case, m is again less than n. So another situation where we have a horizontal asymptote where y is equal to 0. But let me show another example real quick. Let's say we have r of x is equal to 2x squared minus x over x minus 1. X minus 2. All right, so here I have a high power on the top of 2. That's my m value. I have a high power on the bottom of 1. That x has an assumed power of 1. The relationship here is that m is greater than n. So therefore, we would say that there is no horizontal asymptote. And I'll just show you one where, the one condition we haven't met yet. So. Let's say we have this expression, 3x to the 4th minus 2 over 5x to the 4th minus x. The highest power on the top is a 4. We call that m. The highest power on the bottom is also a 4. That's our n. The relationship here is that m and n are equal to one another. So in this case, the horizontal asymptote is going to be the ratio of the leading coefficients. So y would be equal to, so I'd look at the leading coefficients. In this case, 3 and 5, the ratio of those two things. So I would just divide them. All right. So 3 over 5. All right. So that one's got a little extra something going on, but you could also pick out, you know, it's for 3/5, it's going to be a little on the trickier side, but you could also pick out what the horizontal asymptote is graphically. If you plot the graph, so r of x is equal to, again, it's 3x to the 4th minus 2 over 5x to the 4th minus x. All right, so yeah, this funky graph, it's crazy to look at. But if I want to know what this line is approaching, I said line because it looks like a line, but it's really a curve. I can drag along it and I'll get a good sense after a while what it's approaching in terms of y. Because again, my horizontal asymptote is going to be a y equation. So as I'm scrolling along, I see that the y value has leveled off at 0.6. It's actually not exactly 0.6. It's just the calculator is rounding into 0.6. But it does appear that it's trying to tell us that the horizontal asymptote is 0.6 in fraction form, 3/5. So you could actually pick it out at Desmos without doing the work too, which is kind of nice. I mean, it's more than kind of nice. It's extraordinarily nice. Hand in hand with that is what's known as the end behavior model, which is much simpler. It's actually the simplest thing, which is why I don't feel bad about tacking it on at the end. We're not going to do the bit about graphing. We're just going to say find the end behavior model. The end behavior model is really, I mean, it's exactly what it sounds like. It's a model that describes the end behavior of a graph, right? The way you get the end behavior model is you take the term with the highest power on the top of a fraction and divide it by the term with the highest power on the bottom of the fraction. So take term with highest power in the numerator and divide by the term with the highest power in the denominator. And simplify. Like I said, it's actually kind of like a refreshing change from some of the nightmarish stuff we've been doing. This is actually pretty easy. So if you look at the term with the highest power on the top, that's the x squared. The term with the highest power on the bottom, the 2x squared. We're going to write y equals, because there will be an equation, x squared over 2x squared, and simplify. All right. In this case, we have the understood 1 in front of the x squared, but the x squareds will cancel away. And so my EBM, very creative with my abbreviations, would be y equals 1/2. All All right. Oftentimes, an end behavior model is the same as a horizontal asymptote. Not always. So we don't want to fall in love with this idea in place of a horizontal asymptote, but very often it is the same as a horizontal asymptote. So in the next one, we would say y equals 2x squared over x squared, the term with the highest power top and bottom. Simplify. My EBM here would be y equals 2, because the x squared will cancel away. And that's it. That's all there is for an end behavior model. Right? What you do with that will be really important when you get to calculus. We'll do some more stuff with that in the second unit, but for now, that's the only skill that we're interested in. Right? And I'll talk to you more in the second unit about why this is important. Same thing with piecewise functions. Just I didn't want to bog you down with too much, like application stuff before a test. So but we'll get there and you'll see why this stuff matters. All right. So at long last,